This is 9.2. We just got done talking about a system of equations in 9.1, and 9.2 is almost exactly the same. It just takes it a little bit further. So, and this title is specifically called two variable linear systems. So we know it just has x and y, and we know their lines. So this is actually, in a sense, an easy question, an easy possible solutions we have. So there's three cases that we need to consider. So case number one is if I graph the lines, they will cross at one point. So there's one solution, and so that's one possible scenario. Another possible scenario is when you graph them, there's no solution whatsoever because they're parallel. And so remember, parallel lines have the same slope. So if you did solve this equation for y equals mx plus b, and you solve this equation for y equals mx plus b, you would see that they are different equations, but they have the same slope. So that means they'll never ever cross because they're parallel. And the last case, case number three, if you graphed the first line, graphed the second line, they would actually be on top of each other, and every single point, at that point, that point, that point, that point, that point, that point, every single point on those lines will actually be the exact same because these are actually the same equation. And maybe if you look at it just for a minute, pause the video and notice, I basically took equation one and I multiplied by something. All right, so I had to pause the video because I had copied that problem down wrong. So I multiplied something by, if you notice this, I multiplied something by, I basically multiplied by -2. And everything is being multiplied by -2. So these two equations are actually the same exact equation. And so there's an infinite amount of solutions in that system of equations. So let's look at an equation like this. Now we talked about an equation similar to this on video on 9.1. So this one, notice they're both in decimals, and if you don't mind working with decimals, you can, but I would recommend getting rid of the decimals. So if I just basically multiplied, if you notice the first equation, everything has two decimal places. So I'm going to multiply everything by 100. Remember, what you do at one side of the equation, you do the other. So I'm going to move all the decimals two decimal places. So this literally becomes 2x minus 5y equals -30. Similarly with the second equation. So I have 3x plus 4y equals 104. Now I can solve that system of equations. And I'm going to use elimination with this. And if you notice, I'm going to multiply, depending on if you want to cross out your x's or your y's, I'm going to choose to cross out my x's. So if I want my x's to be the same, then I need to multiply them by something to get them the same number. So I'm going to multiply this top equation by 3, and I'm going to multiply this bottom equation by -2. That way, the x on the top will be 6x, the x on the bottom will be -6x, and then they're going to cross out. So this is going to be 6x, the top equation will be 6x minus 15y equals -114. The bottom equation will be -6x minus 8y equals -208. Now, if I add the two equations, the x's will eliminate, and you have -23y equals -322. And then you can solve that, and y equals +14. And remember, I'm trying to find a point. If I graph these, they're going to cross at a certain point, and the y equals 14 is the y part of the point. And then you just substitute that back into one of the original problems, or again, this right here and this right here, those are the original problems. I just multiplied by 100 to be able to get rid of them. So you plug 14 back in, and you're going to get x equals 16. So 16 and 14 is the point, and you can check it. During a test, you can or quiz, you can check that. See that's your x, that's your y. So plug them in right here, plug them in right there, and it should equal -0.38. Same thing with plugging them in right there, plug them in right there, and it should equal 1.4. You can double check that, especially with the calculator. It's not that big of a deal to check those. All right, so let's look at a word problem. And so you may want to pause the video to make sure you copy this down, look at it, study it, and actually understand what's taking place here. So you have an airplane flying from point A to point B. Okay, so you have an airplane. Wonderful drawing there. So that's an airplane, and it's flying from A to B. Now, airplane travels against the wind. So notice from going from A to B, it's going against the wind, which is going to slow the airplane down a little bit. And then on the way back, it's going with the wind, so it's going to speed it up a little bit. Now, this is assuming that the wind is the same on the way to the from A to B, and it's the same going back from B to A. And it's also, we're going to assume that the airplane is flying at the exact same speed. The airplane itself is flying at the exact same speed. So my ultimate goal is I want to find the speed of the airplane and the speed of the wind. That's what I want to do. I want to find the speeds of the airplane and the wind. So we're going to set up two equations, and then we're going to solve the system of equations. Now, the first thing, I talked about the wind speed. So let's say the rate means speed, so the rate of the airplane is R1. So I'm just going to call this airplane speed. And I'm going to say the rate of the wind is R2. So this is wind speed. And notice when you're going against the wind, you're going to have the rate of the airplane minus the rate of the wind, and that's going against the wind, and going with the wind is R1 plus R2. So this is against, and this is with the wind. What we're going to do after that, if you notice, we're going to use the formula D equals RT. D equals RT, distance equals rate times time. We're going to use that. And we know that on the way to the way from A to B, the first trip, from A to B, D equals RT. And we're going to set this up. So we know the distance is 2,000. And the rate going from A to B, again, he's going against the wind, so this is the rate R1 minus R2. And at the time, we know that it took 4 hours and 24 minutes. So basically, 4 hours plus 24/60ths. That's what we do know, that 4 hours and 24 minutes. So that's my first equation I'm going to set up. And then my second equation, what I'm going to do is I'm going to do D equals RT as well. This is my second equation. So once they get from A to B, now we're going to go fly backwards from B to A. So again, the distance is still 2,000 miles. It's still the same distance, but the rate going back will be R1 plus R2, and it only took 4 hours to fly back. So notice my two equations that I have. And I'm going to solve those equations, set them up, simplify, and solve, and that way I can find the rate of the wind and the rate of the airplane. So let me simplify the blue equation first. So again, I'm going to take this blue equation, I'm going to simplify. So I'm basically going to add this together, and then use the distributive property. Actually, I'm going to This actually is, if you pull out your calculator, you can see that this right here is 22/5. Okay, add those together, put it in fraction form, it's 22/5. So if I use the distributive property on just the blue, I'm going to do 22/5. Actually, I wouldn't even use the distributive property. I'm just going to get rid of the denominator. So here I have the R, the R1 minus R2. Yes. So to get rid of that fraction, I'm just going to multiply both sides by 5. So here I get 10,000 equals R1 minus R2 times 22. Okay, so here I'm going to end up getting 10,000. We use the distributive property, so 22R1 minus 22R2. Now, by the way, you don't have to do this, but notice they're all divisible by 2. So I'm going to divide them all by 2. So that's, you don't have to do this. So this is 5,000, 11R1 minus 11R2. Again, you don't have to do that, but it does make it a little bit easier. So I'm going to erase that because I just divided everything by 2. Okay. So, and then the red, you can just simply use the distributive property. Well, I'm going to divide by 4. That's 500 equals R1 plus R2. Okay, so notice I took the blue one and I simplified it. I took the red ones, I simplified. And then all I have to do is now solve that system of equations. And using elimination, you can choose to cross out your R1s or R2s. It's totally up to you what you want to do. I would probably solve for R1. And I'm going to multiply everything by 11. I'm going to multiply this bottom one by 11. And that way you have 11R1 plus 11R2 have 5,500. The blue you still have is 5,000. And then you can see that the R2s are going to cross out the system of equations. So you're going to end up solving for, you're going to have 10,500 equals 22R1, which means R1 is approximately, because you're going to end up getting a not so favorable answer here. So R1 is approximately 477.27 miles per hour. Okay, remember R1 is the airplane speed. So that's why it's like so fast. That would not be the wind. The wind would not be 477 miles per hour. All right, and then you can plug that back in to find the R2, and R2 is the wind speed, and the wind speed is approximately 22.73 miles per hour, which is still pretty windy. But that's how you set up a system of equations. And again, I would suggest you go back and look at the problem, practice setting up. Like, how do you set that up? How do you use D equals RT? Especially this against the wind and with the wind, the air speed. How does that affect the speed of the airplane? And then, of course, just the math alone, using the distributive property, not having a bunch of decimals in the problem, just make sure you practice that and make sure you know how to do the getting to the answer. Specifically, once you get down to here, it should be pretty easy. So that's using a system of equations.